Let's talk about Project 4, Lesson 16. So before we begin, notice that your project has an introduction that's kind of important to understand the theme of the questions. So this project is all about the solar system, and it tells us that Kepler is generally credited as the first astronomer to recognize the role of conic sections in describing our solar system. Kepler's first law of planetary motion states that the path of every planet is an ellipse with the sun at one focus. As the ellipse is sometimes so close to a circle, a simplified version of the path can be modeled by a circle. So we're going to answer the project questions regarding the paths of the planets around the sun. Okay, so here's our question. It tells us that the orbit of Venus is nearly circular. An astronomer develops a model for the orbit in which the sun has the coordinates -520, and the circular orbit of Venus passes through 6220. And each one of the units represents 1 million miles. So we need to find an equation that represents the orbit of Venus according to this astronomer. Okay, so what information do we know? Well, first of all, we know that the sun is at this coordinate. So I'm going to have our sun at -520. And I'm told that Venus passes through 6220. So at this moment in time, we'll say that Venus is right here at 6220. Now the orbit of Venus is nearly circular, okay? So if we wanted to draw this orbit, it would look something like this, okay? And we want to write an equation that represents this orbit. So what do we need here? Well, we need our equation for a circle, right? So the general equation of a circle with center HK and radius R is what? Well, it's x minus h quantity squared plus the quantity y minus k squared is equal to r squared. Okay? So the circle is Venus's orbit. Do I know the center of the circle? Well, yes, I do, because the center is the sun. So I know that my center coordinates are -520. Okay, so what about my radius? Well, they didn't give that to me. I need to know the distance between the sun and Venus, but I don't know it. What I do know is a point on this circle, right? So given that, hopefully your brain automatically goes to the distance formula. So I need to use the distance formula to find r. So there's my distance formula. Notice that it uses two coordinates, so x2, y2, and x1, y1. It takes a difference between the x's. There's some Pythagorean theorem involved, which you may have seen in my other videos, and it tells us the distance between these 2 points. So this is what is going to give us r. Now, once we have r, we can substitute it back into our general circle equation, and that will tell us the equation for this orbit. Now, when it comes to assigning the x1, y1, and x2, y2, it doesn't really matter which one you do. So I'm going to assign this one to -520. I'll assign the other one to 6220. You could have done it the other way around, but just make sure you plug everything in correctly. Keep track of your signs within the parentheses. Those are easy to flip. And once you get radius, don't confuse radius for radius squared. Okay, let's move forward. So question 2. According to the astronomer's depiction of Venus's orbit, Venus is an average of how many million miles from the sun? All right, so let's go back to our awesome picture here. So we knew the sun was somewhere here. I believe it was -520. And Venus was over here, which I think was 6220. And Venus orbits around the sun. So what we know about circles is that all points are equidistant from the center, right? Because at any given point, I can draw a line between the point and the center, and I will get the same measurement. And we call that distance the radius, right? We call the distance between the center and a point on the circle the radius. So when they ask us for the average how many million miles Venus is from the sun, what are they really asking us for? So think that over and let's continue. Question 3. Although the orbit of Earth around the Sun is elliptical, it closely resembles a circle. So the orbit can be modeled by x squared plus y squared equals 8,649, where the Sun is at the origin and each unit of the coordinate plane represents 1 million miles. In other words, we're saying that 8,649 in the equation represents 8,649 million miles. So I want to know how far the Earth travels in 1 year as it makes a complete orbit. Okay, let's think this over. So I like to use pictures to help me understand the information. So what have we got? Well, we're told that the Sun is at the origin in this model. So I'm going to draw my Sun at the origin. And then I've got Earth. So this will be Earth. And I know the relationship between, I know the path that the Earth takes, right? Can be modeled by x squared plus y squared equals 8,649. So in this case, x squared plus y squared equals 8,649. This part, the x squared plus y squared, tells me that my circle is centered around the origin. What does this describe? Well, if I compare it to my general equation of a circle, I know that 8,649 is equal to r squared. I know that 8,649 is equal to r squared. And why is that important? Well, because I'm being asked to figure out how far the Earth travels in its orbit. And another word for that is circumference, right? So I know that r squared is equal to 8,649. I know that r squared is equal to 8,649, which means that r is equal to the square root of 8,649, right? So that means at any given time, the distance between the Sun and the Earth is the square root of 8,649 million miles. Now that measurement is important because radius plays into my circumference equation, right? So if you remember, circumference is equal to 2 times pi times r, where r is radius, pi is our irrational number, and we just multiply by 2. So use your information about the radius, plug it into the circumference equation, and it will tell us just how many million miles the Earth is traveling around the Sun.